So here was our notes from Taylor and Maclaurin polynomials that we did before we left, but I know some of you guys weren't here, so I am posting this to help you with the AP assignment that we have due today. So Taylor and Maclaurin polynomials are polynomials that represent functions that aren't polynomials, okay? Because in calculus, our best functions are polynomials. They're the easiest ones to take the derivative of. They're the easiest ones to find the antiderivative of, and they're really easy to perform those calculus operations with. So if we had a function that wasn't a polynomial, all right, where would we begin? So we'd start with the simplest polynomial, which in our case is linear. So really that's just doing a tangent line approximation, which we've done before. So let's look at the function e to the x. And let's center it at 0. You have to be given some type of point of tangency or point where they will equal each other. So our tangent line approximation for e to the x at x equals 0, if we were visualizing it, all right, so there's our graph of e to the x. We've got our point, which is 0, 1, and our slope of e to the x would be the derivative of e to the x, which is e to the x, and at 0 would equal 1. So the slope of the tangent line would be 1. The point is 0, 1. There would be our tangent line, which is not a great approximation. It's close to the curve when we're close to 0. But once we move outside of 0.2, all right, it's really not a great approximation. But this would be our equation. So our tangent line approximation for that one would be y equals 1 plus 1 times x minus 0, because our center in this case is at 0. All right. So 1 plus x, that would be our tangent line approximation for e to the x. But we want to get a better approximation because e to the x is not a line, it's a curve. So if we wanted to find a polynomial, we would increase our degree. So a second degree polynomial is a quadratic. And if we wanted it to be as similar to e to the x as possible, we want it to go through the same point, have the same slope, and have the same concavity, the second derivative value. So we couldn't do that with tangent lines because they don't have a second derivative, but with polynomial or quadratics we can. So we'd have to start with our most general quadratic, ax squared plus bx plus c. The function, e to the 0 equals 1. The first derivative, e to the x at 0 equals 1. And the second derivative, the first derivative here, is e to the 0 equals 1. So we'd want our quadratic to have all those same qualities. And we would end up getting this quadratic. You don't have to go through the process of finding it. I'm going to give you the formula for the Taylor polynomials. But as we can see, the blue parabola is a much better approximation to our e to the x curve, which is in red. Right, if you look at the scale, all right, now we're going by 0.2s here. So we're a much better approximation as we get closer to around like 0.6 and negative 0.6 than we were for the last one. When we moved outside of 0.2, the tangent line wasn't a very good approximation. Okay, so the rule of thumb is to get a better approximation, we're going to use a higher degree polynomial. So polynomials will have a stopping point. When we turn these into series, they go on forever. So a Taylor polynomial and a Maclaurin polynomial are very similar to the series that we've been doing. The series just go on forever. So our formula for the nth degree, and then we'll go through a couple examples. So you have to be given a center. This is centered at x equals a. Sometimes they use x equals c, but we're going to go up to the nth degree. So this is how we would write our Taylor polynomials. So you start with given a function, right? In our case, we were given e to the x, but you could be given any function. You're going to evaluate the function at the center, and that's going to be your constant. Every polynomial should have a constant, even if it's 0. Then you're going to get your linear term. So you take your first derivative of your function at your center, multiply by x minus a to the 1. Then we take our second derivative at the center over 2 factorial, x minus a to the second, and this keeps going until we go to whatever degree we're trying to. All right, so if we want to stop at the third degree, we're going to stop when n is 3. If we want to go to the fifth degree, we're going to stop when n is 5. And just so you know, the difference between Taylor and Maclaurin is a very specific polynomial where the center is at 0. So Maclaurin is a Taylor polynomial. So if you want to follow in the next video for the examples, we can go through a couple of those, and that should prepare you for the AP question that's due today.